Okay, so moving right along to section 1-4. Now we're going to start using probability of compound events and mutually exclusive events. We're going to start again with some definitions. Sorry about that, someone came in my room. Okay, so let's do our definitions here real quick. So, a union of events A and B. So that's going to be the probability that where let me start that over. So that's going to be the probability of event A or B happening. Okay, when we get down to our examples, this will really make a lot of sense to you. Okay, but you have to subtract overlap. Okay, so if I say that you need to choose a red card or a 3, you can do a red card and you can do a 3, but there are 2 cards in that deck that are both a red card and a 3. So we have to subtract the probability of choosing those 2 cards back out, otherwise they're being accounted for twice. Unions of events are also called compound events. Okay, and they don't have to be events that happen together. They can be, like I said, a red card or a 3. They can be two completely different things. Like rolling, you can roll a dice and flip a coin. Okay, they don't have to come from the same, they don't have to be both flipping a card. They can be those 2 different things. What is the probability that if you go to Buckingham and you are a girl or you are on the basketball team? Well, there's boys on the basketball team too, right? If I said a girl and on the basketball team, that would be a different situation. So those are always or situations. Okay, the intersection of events A and B is where you're trying to find the probability of A and B occurring. Sorry, you guys, it's Friday afternoon on the first full week of school. So that probability, you're going to have the probability of A. Now you're going to multiply, because now you're making that situation much more complex. That's the probability of A and B. Okay, these definitions will be down lower too. Up here you had the probability of A plus the probability of B minus the probability of A or B. Okay, disjoint events and mutually exclusive events go together. So the probability in a disjointed event, it means that they have no outcomes that are the same. Okay, they have no outcomes in common. Okay, so for example, a Toyota cannot be a Ford. Okay, it just can't happen. It can't happen at the same time. A car cannot be a Toyota and a Ford at the same time. It doesn't happen. Okay, so the probability for disjoint and mutually exclusive kind of go together like compound and union events go together. Okay, and the probability of A and B happening equals 0. The probability of if you have 20 cars and 20 Toyotas and 20 Fords, out of those 40 cars, none of them can be a Toyota and a Ford. They cannot, that just cannot occur. Okay? Can't be a banana and an apple. Those 2 things can't happen. If you draw a card from a deck, you cannot draw a queen and a 5 at one time if you're choosing one card. It has to be one or the other. Okay? This is just kind of a graphic organizer of what's happening. So when the union thing, you'll see that these are all our possibilities of A. These are all of our possibilities of event B happening. But here's where they've already been accounted for. So if we don't subtract this amount back out, they're actually being double counted. Okay, the intersection of A and B would be where they both happen. A and B is right in the middle. Think of your Venn diagram. You have either or, right? You have, in a Venn diagram, this is where event A is happening, this is where event B is happening, this is where they are both happening. Intersection A and B, there is no possibility that you're going to find an event that occurs in both A and B there. It's not possible because they don't have anything in common. Okay, so here's your formulas from up above. If A and B are any two events, then the probability of A or B is the probability of A plus the probability of B minus the probability of A or B. So or is the big word there. Okay. If A and B are disjoint events, then the probability of A or B is the probability of A plus the probability of B. So let's go with the disjoint events also. Probability of A and B is 0. That can never happen when you have mutually exclusive or disjointed events. Okay? So, for example, when a 6-sided die is rolled, what's the probability that the number rolled is less than 3 or greater than 5? So, less than 3, we have the options of 1 and 2. So, we have 2 options out of 6. Plus, greater than 5. The only option that's larger than 5 is the number 6. So, there's only one option there. Okay? So 3 out of those 6 times, or half the time, you would roll less than a 3 or greater than a 5. And if you think about it, there's the 3 numbers we would have that would be a successful roll, and there's 6 total. 3 out of 6 is 1/2. Okay? A card is randomly selected from a standard deck of 52 cards. Find the probability of selecting an ace or an 8. So we just need to think about that for a second. There's 4 aces in a deck out of 52, and there are also 4 8s in a deck. Can you, if you choose one card, it cannot be an ace or an 8, so we don't need to worry about that. So we're going to just add those totals together. We don't have any overlap. Something's an 8 or it's an ace. So we would have 8 over 52. That can be reduced down, and 4 goes into both of those, so you would have 2 over 13. So 2 out of 13 times you would choose an ace or an 8. Now here's the one I want you to think about. So what's the probability of selecting a 10 or a diamond? Well, there's 4 10s in a deck, right? There's 13 diamonds in a deck. But isn't there a card in that deck that is the 10 of diamonds? So we need to subtract out that card because it's already been accounted for over here. If we don't subtract it, it's actually being counted here as a 10 and here as a diamond. That same card's been counted twice, so we need to back out that duplication. So that's the 10 of diamonds. Okay? So to simplify that, you have 4 plus 13 is 17, minus 1 is 16 over 52. Those are both reducible by 4, so the possibility would be 4 out of 13. Okay. So, when reading this, let's really think about what this is saying. So of 100 students surveyed, 92 own either a car or a computer. Also 65 own cars and 82 own computers. What is the probability that a randomly selected student owns both a car and a computer? So we can say that event A is owning a car, and that event B is owning a computer. So if we think about our formula, which is the probability of A plus the probability of B, but the problem is we also know that 92 own one or the other. Okay, so we have to subtract back out that possibility of A or B, a car or a computer. So the number of cars out of, and we have 100 as our total, the number of cars there is 65 out of 100. The number of computers owned is 82 out of 100. But we have to subtract out the kids who own computers or cars. They've already been accounted for in both of these sections. So we need to subtract out those 92. Okay? So let's do this the easy way. 82 minus 92 is negative 10. 10 from 65 would be 55 over 100. And you can reduce those each by 5, so you get 11 out of 20. So about a 55% chance, okay, that somebody there owns a car and a computer. That is the end of section 1.4, nice and short. And that's it.